Hello, everyone. My name is David Lim. I'm a PhD student in chemistry at Harvard, and today I'll give you a presentation of a recently published work in JAX titled Evolution of Metastable Structures at Bimetallic Surfaces from Microscopy and Machine Learning Molecular Dynamics. Rational catalyst design involves a tight-knit collaboration between experiment and theory. On the experimental side, we have synthesis of the actual catalyst and its testing at reaction temperature and pressure of interest. We also have fundamental surface science studies performed at ultra-high vacuum using well-prepared single crystal surfaces. On the theoretical side, we have modeling using first principles calculations of surface structures and its adsorbates at the atomic level, as well as reaction mechanisms of elementary reaction steps. What's often not discussed as much, however, is materials evolution due to its complexity. The underlying configurational space is very large to be explored, and also the timescale involved tends to be very long. This makes it very difficult to investigate materials evolution at the atomic level. We are interested in dilute bimetallic catalysts. To give you an example, we look at group 11 metal, such as silver. These are at the end of the D block, and they have full D shell, therefore they're not reactive. To the left of them are group 10 metals, like palladium, which are well-known catalysts, very reactive because their D shell is not full. On the left here is an electronic energy diagram computed by density functional theory calculations of hydrogen dissociation process on these surfaces. So on silver, the energy barrier is very high and the dissociation process is overall endothermic, which means that silver is not very active in this process. Palladium, on the other hand, is very reactive because the dissociation is barrierless and also very exothermic. It tends to be too reactive often because it leads to overhydrogenation and other unwanted side reactions. Recently, single atom alloys or dilute bimetallic catalysts in general have garnered much attention. Here, we dope a small amount of reactive metal like palladium, typically at single atom limit, into an inert host like silver. And what happens is we get the benefit of both worlds. That's why it's called bifunctional. We end up with not only a moderate activation barrier, therefore leading to high activity, but also not too strong of an absorption, which leads also to high selectivity. These bimetallic systems are not as simple as one may initially imagine, however. So using palladium deposited on silver as an example, after deposition at room temperature, we anneal the system at moderate temperature, like 400 Kelvin. And then what happens is palladium dissolves into silver for chemical reasons. Palladium has higher surface energy than silver, so what happens is silver preferentially segregates to the surface. This defeats the purpose, however, because we need palladium to be on the surface to do catalysis. What makes the system even more complex is the fact that if we expose the system to moderate pressure of reactants like carbon monoxide or oxygen, they are capable of restabilizing a certain amount of palladium back to the surface because these molecules preferentially bind to palladium over silver. So this is referred to as a reverse segregation of palladium induced by adsorbates. We had an evidence of this from microscopy. So here is on the left showing as deposited palladium islands shown to have fractal-like shapes, and most of them are monolayer high. After annealing at 450 Kelvin, silver atoms in the surface climb out of the surface layer to completely cover the islands and alloy into palladium. And as a result, we end up with a bilayer structure and also an extensive vacancy pit indicated here as level -1. This was very surprising, and we wanted to understand how this happens at the atomic level. So we have decided to utilize molecular dynamic simulation to study this dynamical phenomena. In MD simulation, we move atoms in real time, and to do so, we need force fields or inner atomic potential. Empirical force fields tend not to be so accurate unless they are designed specifically for surfaces. And so what we decided to do is train a machine learning model that can learn and predict atomic forces just from atomic configuration, focusing on 2+3 body interactions. And we utilize so-called Bayesian active learning developed by our collaborators in our group. And what this algorithm does is it uses Gaussian process to estimate prediction error or uncertainty, and that allows us to automate the training process. If the error is high, it automatically performs accurate quantum calculation and retrains the model. If the error is low, that means the model is confident and it then proceeds with the usual MD routine. This has several advantages, and it ultimately allows us to perform large-scale and long time-scale simulations that have not been possible previously. In addition to this force field development, we also proposed an automated workflow that allowed us to characterize atomic level events and mechanisms of restructuring events. So after we perform MD simulation, we post-process the trajectory where we assign all atoms to discrete lattice sites. And that allows us to easily detect whenever Z coordinate of any atom has undergone a change. And this means that a restructuring event has happened. So then we isolate this event and automatically classify it into 7 previously established restructuring event classes based purely on their Z coordinate and coordination numbers. And then we proceed to do a detailed transition state modeling, which allows us to look at detailed energy landscape of each individual event. Here's a video of our simulation looking at Palladium Island, shown here in green, deposited on silver 111 surface, where silver atoms are colored according to their layer heights. This was done at 500 Kelvin, very close to actual annealing temperature, and the simulation was for 2 microseconds. In the beginning, we have rapid exchange of palladium with underlying silver around the island edges. The blue atoms are silver atoms that have now come up to the surface. And over time, silver climbs up to on top of the island and eventually forms a second layer that is now a palladium silver alloy. Over a longer period of time, more and more silver starts to come out of the surface to further cover this bilayer structure. And eventually we end up with a vacancy pit that grows in size over time. And so, as you can see, we have ended up with a structure that is completely different from what we started off. What is essentially happening is palladium wants to dissolve, but cannot do so immediately. So silver instead comes out of the surface to cover the structure first. At higher temperature, we can see how palladium dissolves completely into the surface. So at 900 Kelvin, palladium again is completely covered by silver, and that results in an extensive vacancy pit, similar to what we saw in the STM image. And over a much longer period of time, palladium starts to dissolve layer by layer. And as they do so, silver atom that was covering the palladium now gradually go back into the vacancy pit. And eventually, all palladium is now dissolved. A few atoms occasionally visit the surface, and we end up with silver atoms where palladium atoms used to be at the beginning. Using the algorithm we proposed earlier, we were able to identify 4 main types of restructuring events that were responsible for this phenomenon. And these were in very good agreement with the 7 main classes that we established in our previous study, focusing on single atom palladium in silver. So our next investigation, of course, will focus on developing reactive force fields to be able to simulate systems with adsolbates and their effect on restructuring, such as carbon monoxide and oxygen. At the moment, we're focusing on hydrogen activation and spillover in dilute palladium silver and palladium gold. And this is in collaboration with experimentalists and various theoretical approaches. Yep, so to conclude, I'd like to refer to you to our two publications outlined here that have simulated palladium silver restructuring process for the first time. I'd like to acknowledge funding by EFRC IMASC, as well as computational resources at Harvard and Department of Energy, and our advisors, Professor Krasinski and Professor Sauté, for theoretical efforts, as well as Professor Friend and Maddox for experimental efforts, and our various collaborators in both experiment and theory. Thank you very much.